So for conservation law, okay, this is just some difficult stuff. Okay, just give it. So you know what does the conservation mean? So energy can be transferred from object to another object or transformed. So from one form of energy to another form of energy. So first of all, let's define what is energy. So energy is a capability to do work. So work is energy transfer process by using the force and displacement. So there is another kind of energy transfer. We call it the heat, is it? Heat is an energy transfer due to temperature difference. So just when when two objects at different temperatures are touching each other, then there is some energy transfer. It does not require forces or displacement. So work is another kind of energy transfer. So work is defined as the force dot product with the displacement. Right? You just look at the diagram. I hope you understand. So this is for the constant force. Okay, if the force is constant, then you do it like this. And most likely in your textbook, when you write it like the W equal to Fs cosine theta. Right? The S is the displacement. Cosine theta, the theta is the angle between the force and the displacement. So, and hope you know the mathematics of the trigonometry. When the cosine theta is, when the angle is an accurate angle, then the cosine theta is positive. When the angle is 90 degrees, the work done is 0. And then if the angle is opposite angle, and then it will become, the work done will become negative, just like this. And then this is for the work done. So what does the positive, negative, and 0 work done mean? So for positive work done, it means that you increase the energy of the object. Now we are not specifying which kind of energy it is. We just say that, okay, it increases the energy of the object. If it is a negative work done, it decreases the energy of the object. And then for 0 work done, so that means the energy of the object does not change by this force. Right. So this is a concept of the work done or the work. The next one is a power. I think you have learned it in Form 3. So by talking about the heat, we also have the concept of power. So energy over time, or just say the work over time. And then also for constant F, then the power, we have the formula F dot V. I hope you still remember what is dot product. So just the force times velocity times cosine theta. Remember, okay, these two simplified formula is for constant force. If the force is not constant, in general, you need to do the integration. Then let's have a look at the two types of energy that we are mostly concerned in the topic of mechanics. The first one is a kinetic energy. Hope you still learn a bit about it in the heat. So it is the energy of the motion. So when the object is moving faster, and it has a larger kinetic energy. So let's see how we can derive the formula for the kinetic energy. So make it simpler, okay? So let's say the initial velocity of the object is 0. And then you apply the force on it. And then to move it to travel for a distance s, or the displacement s. Constant force by constant force. Now you know this force will increase the energy of this object. And the energy it increases is the kinetic energy because the object is moving faster and faster and faster. So, and it's very natural for us to let the kinetic energy to be 0 when the speed is 0, is it? And then, so the work done is a change in energy. So in this case, the work done is the final KE minus the initial KE. That's a change in energy. So just for simplicity, I just let it to be zero. I just let the speed to and the kinetic energy to be zero initially, and then you get Ke to Fx. So you know F can be written as ma by Newton's second law, and by using the equation of motion, by using v squared equal to u squared plus 2as, then a times s can be written as half v squared minus 0 squared. So therefore, we get the kinetic energy of the formula that is half mv squared. Okay. No question. Now you can see it, okay, because sometimes the velocity can be written, we use the plus or minus sign to represent the direction of the velocity, but it doesn't matter here because you take the square. So the kinetic energy will be always positive. It can't be negative in the sense of physics and also mathematics. The next term, the next kind of energy we concern is a potential energy. Potential energy is the energy related to the position. So let's say if you extend the rubber band, so you store some elastic potential energy in the rubber band. But let's say if you move an object to a higher position, then you increase the potential energy of the object. So this is the energy that yeah. Then let's see how we derive the formula. Okay, maybe we just skip how we derive it. Okay, it doesn't matter really. It really doesn't matter. But just for you to get the idea, okay, to get the integration, okay, it means just finding the area under the curve. So let's say for the elastic potential energy. So you know the force has a formula F equal kx. K is a spring constant and x is an extension. So then you find this area. Okay, this is x, this is F equal kx. It's quite simple, is it? This area. So just half kx times x, then you got half kx squared. So this is a formula for the elastic potential energy. Now, and also you can also see that, okay, the potential energy is proportional to x squared. So what does it mean? So it means that, let's say if you extend the spring or a rubber band, let's say when you expand the x from 0 to x equal 1 cm, let's say 1 cm, and when you extend the extending from 1 cm to, let's say, 2 cm, the energy required are not the same. You can calculate by substitute the value inside. Okay, then the amount of energy required will be this energy multiplied by 3 will be the energy of this one. It is not linear. The longer the larger extension, and then when you the more energy you require to extend it further. So this is an elastic potential energy. The next one is a gravitational potential energy. We use this formula for gravitation when we are talking about a celestial object, or when the object is very far away from the Earth's surface. So most likely we're not considering this one right now. So most likely we are talking about the object with the constant magnitude of weight. So that's mg. And then the potential energy of the object gain will be just mgh. The force times displacement. So you just consider the force times displacement. So that is mgh. Just have a look at here, okay? The h is the increase in the height. So this is talking about the vertical displacement. So that means, what does it mean? So let's say if your object is moving from this place to this place, from point A to point B or to point C. Now, no matter whether it follows the path, the first one, the second one, or the third one, consider B and C are at the same height. The increase in the potential energy are the same for these three different paths. So you just need to consider the increase in the vertical height. Okay, then that's a formula for the potential energy. Then what is the importance for us to learn the potential energy? So let's say if we just draw a curve. If you want to find, so let's say this curve is smooth, so that means there's no friction acting on the object. So when the object slides to the bottom, okay, so there will be the potential energy of the object will decrease, and it will gain the kinetic energy. So let's say if you want to find a speed at the bottom, so there's several ways that you can do it. You can consider the force and using the equation of motion. It's not easy to do because first of all, you know that for the equation of motions, there are two criteria for you to use it. So one is a constant force, constant acceleration. Another one is a straight line motion. In this case, it's neither straight line motion nor constant acceleration motion. So you cannot apply the equation of motion in this case. And then what should I do? I say okay. So and it's not easy for you to use force and equation of motion, but by just considering the energy, okay. So let's say it released from the seals released from west from the highest point, and you want to find a speed at the lowest point. So energy, if you apply the energy, it doesn't matter whether the path is straight line or not. So you just first of all, you need to know how the energy transform from one kind to another kind. So this one, the gravitational potential energy is converted to kinetic energy. Then the gain in kinetic energy will be half mv squared. The loss in the gravitational potential energy will be mgh. So let's say if the initial speed is not zero, there's some initial speed here. Then you just get the left hand side is a loss in GPE. The right hand side is a gain in KE. So the gain in KE will be the final KE minus the initial KE. You can still find the speed at the bottom. So that's u square root u square plus 2gh. It doesn't matter how the curve looks like, okay? It can be a straight line, it can be a curve, it can be a straight line like this. It still gives you the same answer. Okay? So most likely, if the path is a curve, then you apply the conservation of energy in the question. Okay, so this is just one example. I think this is really simple example. So similarly, if you want to throw a ball upwards with the let's say initial speed 0. So let's say if you want to find the maximum height it can attain, it can reach. So at the maximum height, the speed of the object will become 0. Then the height will, let's say the height is h. then the change in kinetic energy, that's half mu squared, that will be your mgh. Then you can get the height to be 2u squared over u squared over 2g. Okay, I think these two are very simple examples. I can capture a screen and let me clear it in 5 seconds. 5, 4, 3, 2, 1. Done. The mass is 2. No, I did not take any value of the mass. You can see either in this equation or either in this one or in this equation. The mass can be cancelled out in the equation. The mass doesn't matter. So that means no matter what value the mass is, how massive the object is, it still gives you the same height. It still gives you the same velocity at the bottom. Okay. So 5, 4, 3, 2, 1, done. So let's give you another example. Let's say there's a spring. So let's say the object is moving initially with the speed u and towards the spring. Let's say the spring is initially it's not compressed initially. Okay, so that means it's at its natural length with the spring constant k. So in this case, the spring will be compressed. And then let's say we want to find a maximum compression of the spring. Now we can't use the equation of motion in this case because the acceleration is not constant. So Fu kx, then the force depends on the compression of the spring. The larger the compression, the larger the force. That means the larger the acceleration. So that means the acceleration is not constant. Okay. Then let's move on. Then let's say how then it loses the object. So at its maximum compression, the object will loses all its kinetic energy. And then all the kinetic energy is converted to the elastic potential energy. So that is a formula half kx squared equal to half initial k the change in ke, half mu squared. Then you can get the compression of the spring to be square root m over k times u, is it? Okay. There's also the case when the initial compression, let's say it is not 0, but we can still apply the formula of the apply the kinetic energy. So let's say the initial compression is y, then you just get here is the change in elastic potential energy. Then you get a similar thing for it. So I think I almost give you those essential examples here. So then let's go back to your note. Have we ever talked about the circular motion? Do we? You may also have a look at these examples. So there's also an approach for you to do it by using equation of motion. But you need to cut the path into infinitely many straight line paths. And then so you can do it like that. So just see same as what I've done. So let's say if there's also some energy loss, so let's say there's a friction. So you can still do it, but you need to know how the energy transform. So let's say if there's a friction with the constant value friction. So you know the potential energy is lost, and then the Ke will be it will gain kinetic energy, and then parts of the P lost will be converted to will be the energy lost. So let's say there's a friction. Then the energy lost by friction we call the work done against friction. So the work done is you use the formula the Fs cosine theta. So but for the case of the friction, the work done will always become is the friction times the distance travel, not the displacement travel. Why the case is like that? Because the friction is always tangent to the path. So in this case, you take the distance travel. So that means the length of the path matters. And then you can write down the formula like this. We haven't talked about it. We haven't talked about the circular motion, is it? If no, let's skip it first. And tomorrow, then let's talk about the momentum. And then Wednesday, we do some exercise about the energy and momentum. And then on Thursday, we go to gravitation and circular motion. And then on Friday, I will skip this topic for your conversion. Okay, I think we really don't have time to cover this topic before this conversion. So on Friday, we'll just do some more past papers. Yeah. Okay. And then just have a final revision on this commission. It's fine if you don't get a prize in this commission. If you get one, that means yeah, I will be very happy. And it's fine. Then